In the previous couple of videos, we've looked at how to write electronic configurations for atoms of different elements. We've learned how to write electronic configurations for ions, and we've learned how to write shortened versions of electronic configurations using the noble gases. In this video, we're going to add a little bit more detail to these electronic configurations by looking specifically at how the electrons fill each of the orbitals within the sublevels. We're going to use a thing called an electron spin diagram to show this. Okay, so what the hell is an electron spin diagram? Okay, well, there are two key aspects of electronic structure, which describes to us how electrons fill the orbitals that they occupy. Now, we've already seen the first one, and the first rule is that two electrons can go in each orbital providing they have opposite spin. We saw this earlier. I'll remind you where we saw it. It's up here in red. It's this one, sorry, where are we? It's the Paulie exclusion principle. So that was rule one. Orbitals can hold electrons of opposite spin, and this is two electrons, sorry, of opposite spin. This was the Paulie exclusion principle. We then looked at this one, which showed us rule two, and that's electrons always occupy the lowest available energy first. This is the Aufbau principle. And essentially what we're looking at here is a third rule, and that is this in red here. When orbitals of equal energy are available, so within one sublevel, if there are more than one orbitals, for example, in a p sublevel or three orbitals, electrons will occupy each orbital singly before filling them in pairs. So this is known as Hund's rule of maximum multiplicity. Okay, so what does it say? Again, it says when orbitals of equal energy are available, electrons will fill them singly first before filling them in pairs. So my class note that that's in red, that means it needs to go into your dictionary. So pause the video and write that down now. Okay, so what does this mean? Okay, well, just say we have electronic configuration for, say, example, we're talking about lithium. We know that lithium has 3 electrons, like this, and we know that the electronic configuration then for lithium is Li, and it goes like this: 1s2, 2s1, and that's the electronic configuration. That's 3 electrons altogether. But if we were to show what's going on here in terms of using what we call an electron spin diagram, it would look like this. We would use a box to show each orbital. So there's a box to represent the s orbital in the 1s sublevel, and here's a box to represent the s orbital in the 2s energy level. So how do these electrons fill up these orbitals? Well, we know the first rule is that 2 electrons can go in each orbital and they must have opposite spin. So how do we show this? Well, the spin options are what we call spin up, which looks like this, an arrow pointing up, that's spin up, and electrons can have spin down. So they are opposite in spin, one up, one down. Okay, so that's how electrons will fill orbitals. And there's 1 electron left. You can choose to draw this whatever way you want. It can be up or down, okay, because there's only 1 in here, so it doesn't really matter whether it's up or down. I'm going to draw it up. This would be a correct spin diagram for lithium. This is correct. Let's look at perhaps an element that has more electrons. Let's look at, say, for example, boron B. Boron has 5 electrons. So the electronic configuration. We're just going to start by drawing the spin diagram. So here is the orbital in the 1s sublevel. Here is the orbital of the 2s sublevel. And then in the next sublevel is the 2p, and I know that the 2p has 3 orbitals. So I'm going to draw 3 boxes. And I know that each of these boxes represents an orbital of equal energy. So how would I do this? Well, the 5 electrons, I know that 2 go in the 1s. And they're opposite spin, so I'll draw them like that. That's like 1s2, like that. 2 go into 2s, like this, and it's 1 spin up and 1 spin down. And then 1 goes into the 2p sublevel, like that. Okay, so this is 2p1. And again, it doesn't matter. You can draw it spin up, or you can draw it spin down. Doesn't really matter because there's only 1 electron in there. So what then? So this is a correct electron spin diagram. This is correct. What then about an element with 1 more, say carbon? Carbon has 6 electrons. So what happens next? Okay, so again, spin diagram for this. Here is the orbital of the 1s sublevel. Here is the s orbital of the 2s sublevel. And, oh, sorry, no, not 2s2, that's just the 2s. And then here again is the 2p sublevel with 3 orbitals. So 1, 2, 3 boxes like that. This is the 2p sublevel. Okay, so same thing. We occupy the lowest available energy level first. So 2 go in there. 2 go in there, opposite spins. And now we've got 2. And this is where Hund's rule comes in. We don't do this 1, 2 in that first orbital. That's not correct. Okay, the reason why it's not correct is because Hund's rule said is when equal orbitals of equal energy are available, electrons fill them singly first before filling them in pairs. So that there is not correct at the moment. Okay, so what I'm going to do is I'm going to fix it. So I'm going to get rid of that, and I know it fills them singly. So I'm going to go to the next orbital. And again, there's 2 options here. You could draw it spin down, and that would be wrong as well. The reason why that's wrong is the electrons will arrange themselves in the same spin as they are in other orbitals. So it can either be spin up or spin down, but both of these have to be the same. So because I drew the first one spin up, I need to draw the second one spin up. All right, so it's getting a little bit complicated. It's more important that you remember that you have to fill them singly than in pairs. So it was incorrect when I had one up, one down, because they're in different orbitals and they should be the same there. Okay, so this now is correct. Okay, so what if I have an element with 8 electrons? Say we had oxygen, 8 electrons. Okay, well then we're going to go ahead and draw the spin diagram again. So here is the 1s, here is the 2s, here is the 2p, 1, 2, 3, and then we've got the 4s. So no, not the 4s, the 3s. There's 2p and here's the 3s. So actually, I don't think I'm going to need to go to the 3s. I don't know what I'm doing. Sorry, don't need the 3s here because I don't have enough electrons. I've only got 8. So let's go ahead and do this. We fill up the lowest available energy, which is the 1s. So there's 1s2 like that. That will be 1s2. And spin up, spin down into 2s, 2s2. And then we go, okay, there's 1 electron, 2 electrons, 3 electrons. How many is that altogether? I've got 4 and 3 is 7. That's 7 electrons. So I fill them singly. After I fill them singly, I've got 1 left. I go back to the first orbital in the p sublevel and I fill that with a second one that's opposite spin than the first one in that orbital. So this will be 2p4. Okay, now another thing to note is that each of these boxes represents a different orbital. This would be the px orbital, this would be the pz orbital, and this would be the py. This would be the p. Sorry. Making a mess of things here. Let me get rid of that. Px. This one is probably the py, and then this last one is the pz. Okay, so each box represents the 3 different orbitals. If I was doing a d sublevel, I would need 5 boxes. Okay, because there are 5 orbitals in a d sublevel. So I'm hoping you've got the idea here. If not, you might need to go back and watch it again when you're doing the questions. Okay, so what I want you to do is have a look at these questions. So 295, it says complete an an energy sublevel spin diagram for each of the following elements. Hint, it may be helpful to write out the configurations for the elements first. Remember, electrons go in pairs with opposite spins. Orbitals with the same energy are occupied singly first. So you do need to follow the rules, the 3 rules we've learned so far. All right, so go ahead, pause the video and do 295. Okay, so you should only be watching if you've done 295. We will be going through them in class the next day. Let's take a look at 296. Which of the following diagrams represents the electrons in the ground state of a boron atom? So which one is correct for a boron atom? All right, so it might help you to actually do out the spin diagram here, or you may be able to look and see and just tell yourself which one is right and which one is wrong. So pause the video, write down the answer to that. Okay, and now we've got a couple of extra questions here. These are the Bohr electronic structures. So this is when we were drawing Bohr atoms of these things, these 5 different things. Okay, so I don't think that needs any explanation. Pause the video and do them questions now. Okay, so that's it, guys. Hopefully you understand electron spin diagrams. You can see how it adds more detail to the electronic configurations. And sometimes you are asked to talk about the electrons within a specific sublevel and talk about how they are arranged. And again, that's the way we would do it. We'll draw an electron spin diagram and explain that they fill orbitals in singly first before they fill them in pairs. All right, guys, that's been electron spin diagrams. I'll see you in the next video.